Hello students, now in this subunit I am going to discuss another type of charge source or radiation source, that is heavy charged ion source. Basically in this case a nucleus is emitting a particle which is heavier compared to an electron and is ionic in nature, and it is heavy and positively charged ion, and it can be of different varieties. So what are the different types of heavy charged ion sources? First is the alpha decay, that is a nucleus which is radioactive is decaying through emitting alpha particle, which is a nucleus of a helium 4 atom. Or other source of charged ions is spontaneous fission, in which a heavy nucleus splits into two lighter nuclei, and both of them are ionic basically in nature initially, and later on they capture electrons and become neutral. So let us start with the alpha decay. So alpha decay is represented by this process in which a nucleus species X with mass number A and charge number Z converts into a nucleus species Y with mass number A minus 4 and charge Z minus 2, and along with it an alpha particle is emitted with mass number 4 and charge number 2. So alpha particle is basically a helium 4 nucleus. So what is happening is the X is converting into a lighter Y nucleus, and the difference in the atomic mass in the atomic number is emerging in form of the atomic mass and atomic number of the alpha particle. Heavy nuclei are energetically unstable against spontaneous emission of alpha particles. So basically spontaneous emission of alpha particle takes place because heavy nuclei are energetically unstable. And what happens is that the alpha particle comes out through the nuclear barrier, and it is the probability of decay which is governed by the height of the barrier and the energy of the alpha particle. So the half-life of useful sources can vary from days to many thousands of years, depending upon the barrier and the energy of the alpha particle. So basically an alpha particle comes out of the barrier through a process which is known as tunneling, and which is a barrier penetration mechanism. So alpha particle does not have sufficient energy to cross the barrier, but it can tunnel through the barrier through the quantum mechanical tunneling process, about which we will discuss briefly in the later units. The alpha particle energy appears in either monoenergetic form, in one energy or group of energies, and all those groups are practically monoenergetic. So any distinct transition between the initial and the final state, that means between the ground state of the parent nucleus to the ground state of the daughter nucleus, a fixed energy difference or Q value is there which characterizes the decay. So, and actually X is converting into Y, and in the process some energy is released, which is the difference in the energy of the two nuclei, and that energy is basically the Q value. And this Q value is shared by the recoiling nucleus Y and the alpha particle. And this sharing is always unique. So alpha particle always gets an energy Q times A minus 4 divided by A. That is the Q value of the reaction into A minus 4 divided by A, where A is the mass number of the parent nucleus. Here in this figure, I'm showing for a process in which a plutonium-238 converts into uranium-234 through alpha decay, and there are three different energy levels. Alpha particles of three different energies come out because plutonium converts into uranium, and there are three levels of uranium into which the plutonium gets converted, and in each level an alpha particle of different energy is basically produced. So here in the y-axis you have the counts, that is the number of alpha particles that are coming per for a given energy, and here you show the detector channels, that is the detector energy window in which the detector is actually detecting the incoming radiation. So basically here you can see there is a peak here, that means in this energy range an alpha particle of energy 5.358 mega electron volt with this much of counts, that is 10 raised to power 2 counts per detector window are produced. Similarly here another channel alpha particle of energy 5.456 mega electron volt is produced, which has got a higher detector count. And similarly another channel of alpha 1 particle rather, has an energy of 5.499 mega electron volt, and it is having a higher number of counts. So higher number of alpha 1 particles are produced compared to alpha 2 and alpha 3. The half-life of this source is 86 years. So here we are showing different sources like gadolinium or thorium or uranium. Each one is having a half-life of different years, like GD 148 is having a half-life of 93 years. Similarly, thorium 232 is having a half-life of 1.4 into 10 raised to the power 10 years, and so on. Similarly, the energies of alpha particles that are emitted is also shown in this table. For example, in the case of GD, the energy is 3.182787 MeV and 100% branching ratio. So a monoenergetic alpha particle with 100% probability with energy 3.182787 mega electron volt is produced. Whereas in case of thorium, which is a half-life of 1.4 into 10 raised to the power 10 years, two different channels are there, each with probability or percent branching 77 and 23%. So one branch of alpha particle has an energy of 4.012 MeV, and the other branch is having an alpha particle energy of 3.953 MeV. So 23% of alpha particles are produced with 3.953 MeV, and 77% of alpha particles are produced with 4.012 MeV. And here you are also shown the experimental error bars. So you can see in this table, which you can refer by pausing the video, there are different types of nuclear species which are undergoing alpha decay. Now, it is seen that most of the alpha particles are having an energy between 4 and 6 MeV. So why is it so? Because of the penetration taking place inside the barrier, or the tunneling process that is taking place, which produces an alpha particles outside the nucleus, and there is a strong correlation between the alpha particle energy and the half-life of the parent nucleus. If the energy of the alpha particle coming out is high, that means the alpha particle is at a higher level inside the nucleus, at a higher energy level inside the nucleus, so it has more probability of passing through the barrier. So it has got a higher probability of passing through the barrier, so its half-life is smaller, because more the number of alpha particles are coming out within a given time period, because the probability of penetrating the barrier is more. Whereas if the alpha particle are having a lower energy, then the probability of penetration is low, so the half-life also increases. So the half-life becomes more if the alpha particle is actually of a lower energy. And that you can see from the previous slide, the energy of the alpha particle has got a strong correlation with the half-lives, which you can pause and reverse the video and you can see the half-life and the energy correlation. Generally, alpha particle loses energy rapidly in the material. So the alpha particle sources have to be very thin. So since the energy is coming out monoenergetic, alpha particle sources have to be very thin, and so that that energy is not absorbed by the material or the source material itself. Second type of charged particles that come out is through the spontaneous emission. All heavy nuclei are in principle unstable against spontaneous fission. So all the heavy nucleus can decay into two lighter nucleus, can split into two lighter nucleus or two lighter fragments because they are inherently unstable. And the stabler lighter nucleus can be produced by the property of energy reduction. But only some of them are spontaneously fissile. Most of them have to be bombarded with neutrons and then they get fission. So then the ions that are produced or the fragments of the nuclei that are broken up, they are of a mass greater than that of alpha particle. They are much heavier compared to the alpha particle. So each fission splits the nucleus into two fragments, and from the conservation of momentum, these two fragments move in the opposite direction. Now, since they are moving in the opposite direction, and if the source or the parent nucleus is basically deposited on a thin film, one side of it would be absorbed by the film itself. So only one side comes out. So the one of the fragment comes out, and the other fragment, which is moving in the opposite direction, is absorbed by the film on which the source is deposited. Here in this figure, it is shown that for CF252, different types of fragments are shown. So basically, you can see the relative probability of different fragments of different mass numbers, and for this CF252 spontaneous fission. So you can see that some maximum number of fragments are coming from this mass number, which is 105 or 106, and the other maximum number of fragment is of the order of 1045 or 1050 mass number. So basically the splitting is you can say asymmetrical. The symmetrical splitting, in which both the nuclei are of the same mass, which is around 120, has got the least probability. So most probability is for the asymmetrical splitting, in which the two fragments are having different mass numbers. So these fragments initially, they are positive ions. So they are basically radiation of positive ions with net charge approaching the atomic number of the fragment. So basically the fragment's atomic number is also the charge of the ion that is coming out. But gradually, as they pass through the medium, they start absorbing electrons from the surrounding medium. And so that reduces the effective charge of the split up fragments. So that is the reason you are having ions of different charges that are coming out during the splitting or the fission process.